a screening tool for cardiovascular disease management in resource-constrained environments. Congenital heart diseases are the most common type of birth defect. 1 out of 100 live newborns are born with heart defects. In Sri Lanka, more than 3,000 kids are born with CHDs annually, and among them, about 1,500 deaths occur due to the lack of facilities. The commonly available diagnostic tool for CHD identification is the stethoscope, which is used to listen to heart sounds. But it requires expertise to identify the CHDs by listening to the heart sounds only, and it is even more difficult to do so in noisy environments. On the other hand, there is the echocardiogram machine, which uses ultrasound imaging of the heart to view and identify a defect in the structure of the heart. However, it is time-consuming and expensive. Therefore, there exists a need for a diagnostic tool that can overcome the challenges of these two methods. A brief survey was conducted to verify this problem, and most survey participants agreed with the requirement of simultaneous ECG and PCG acquisition, as well as adaptive noise cancellation in a diagnostic tool. So why do we need ECG and PCG simultaneously? PCG is the waveform of the heart sounds. It represents mechanical activity and the structural information of the heart. ECG, on the other hand, represents the electrical activity of the heart, which provides functional information. When combined, simultaneous ECG and PCG can give us more detailed information about any defects of the heart and its valves, along with the exact location of that defect in the cardiac cycle. With that, we identify that there exists a need for an accurate, reliable, and noise-filtering screening tool that can simultaneously acquire synchronized ECG and PCG signals, which also provides the ability to visualize them in a user-friendly interface. The system of the screening tool consists of 4 main blocks: the acquisition of ECG, PCG, and SpO2 signals, processing and transmission, analysis of the captured data, and the power management system. This is the PCG denoising pipeline. PCG and ambient signals are sampled at 8 kHz, downsampled to 2 kHz, averaged, and then filtered. The first plot is the noisy signal. The left shows the real-time filtered signal, and the right shows the offline filtered signal. The ECG denoising pipeline removes baseline wandering and power line noise. The left plot shows baseline drift, which is removed in the filtered signal on the right. Next, we will look at a live demonstration of our device prototype and the GUI interface. First, we must insert the finger into the SpO2 sensor and plug the attachment to the device using the cable. Next, turn on the device using the switch and keep the stethoscope head to the chest. Here, we must ensure all the electrodes are properly connected to the body, otherwise a lead-off warning will be shown in the interface. Now, you can see the real-time simultaneous PCG and ECG signals in the GUI interface. To denoise the signals, you can enable the filters using this checkbox. Now you can see the denoised PCG and ECG signals. Now, let's look into our mobile application. First, the user must sign in to access the dashboard, then connect the device using Bluetooth. Here, users can adjust the recording settings. Next, place the device, start recording, and see signal visualization on the screen. Then save the recording under the patient. To review a session, select the patient from the list and play the saved recording. The PhysioNet 2016 Challenge Training A dataset is used to train the classification model to identify any cardiac abnormalities. Since the goal is to solve the classification problem as an image classification problem, to represent the signals as images while preserving their temporal and spectral characteristics, scalograms are generated. Our classification model features a 2-branch architecture that processes ECG and PCG scalograms in parallel, using convolutional layers. Intermediate features from both branches are fused progressively to generate an additional feature vector. The 3 extracted feature vectors are added and sent through dense layers for classification. This design allows the model to learn complementary information from both signals. Our model achieved a high sensitivity of 94%, which is desired in medical diagnostics. Despite its strong performance, the model requires lower computational and memory resources, making it suited for resource-constrained settings. In conclusion, congenital heart defects remain a major health concern, especially in settings with limited access to advanced diagnostic tools. Our device offers a practical solution by capturing clean ECG and PCG signals simultaneously, supported by real-time visualization and a machine learning model, making cardiac screening more accessible.